Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at proofs. So one of the things I love about mathematics is it's the only subject in which you can prove something definitively. So let's look at an example of this. We're going to prove that the square of an odd integer is always one more than a multiple of 4. So in order to prove this, we need to write an arbitrary odd integer as an expression. So you can write any odd integer in the form 2k plus 1, where k is itself an integer. That's the definition of an odd integer. It's one more than an even integer. So an even integer can be written as 2 times some integer, like 14 is 2 times 7, 32 is 2 times 16. So this is going to represent an arbitrary odd integer. So we want to prove that its square is always one more than a multiple of 4. So what we're going to do is square this. So using our rule for binomial squares, we square the first term, 2k times 2k, we square the last term, and in the middle goes 2 times first term times second term. 2 times 2k is 4k, times 1 is still 4k. So, of course, we know that 4k squared plus 4k is a multiple of 4. 4 times k squared plus k, this is a multiple of 4. It's divisible by 4, because if we divide by 4, we're left with k squared plus k, which must be an integer. So what we have, we can write k squared plus k as m. So if you square an odd number, it will be in the form of 4m plus 1. 4 times an integer plus 1, where here m equals k squared plus k. So this proof actually relied on quite a number of facts that we know about the real numbers. So for example, how do I know that, say, this will be an integer? How do I know 4k squared plus 4k is an integer? Well, that's because integers are closed under addition. So we know that if you add two integers, you get another integer. So that there, called closure, when we saw that when we're looking at rational and irrational numbers, closure is an axiom of real numbers. You can't actually prove it true. We rely on that to prove other statements. This also, going from here to here, relied on the distributive law, which is another axiom of real numbers. So the important point to note here is that whenever you are proving something in maths, you're proving it in the context of what you assume to already be true. So for the real numbers, there are a list of things that we assume are already true, like that addition and multiplication is commutative and associative and distributive. We rely on those facts to be able to prove something. There are other systems in which they start with different axioms, but it's really important that we understand when we're proving something, we are just making an argument that is beyond flaw. It's flawless, no one can poke a hole in it. But those arguments are going to rely on assuming that other things are true. This is only true because of properties of the real numbers, like being closed under addition, like the distributive law holding, and so on. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.